In this video, we will teach you great power, and so of course great responsibility is required. Okay, what's the power here? The power is to calculate, will something happen? So this is incredibly powerful stuff. We just need to calculate delta G, and remember that as soon as it's less than 0, it will happen. If it's equal to 0, it will be at equilibrium, and if it's positive, it cannot happen thermodynamically. And if it says thermodynamically it can't happen, it can't ever happen. So the question is, in the last video, right, I gave you delta H and I gave you delta S, so how do you calculate these? Well, if you remember back to Chemistry 1, we went ahead and we showed that the heat of a reaction can actually be calculated under standard conditions by summing together the standard heats of formation for the products, making sure to multiply by the number of moles of product we have, and doing exactly the same thing for the reactants. Okay, and what we're actually doing here is we're imagining the chemical reaction. So we're starting with reactants and we're going to products. And instead of doing that, we're actually going via the elements. And if you remember the little F here, the F here stands for formation. So this is the reaction where you form a compound from its elements. So if you imagine going from reactants to elements, you're essentially unforming your reactants. So it's delta H of formation for your reactants. The minus there is telling you that you're unmaking them. You're turning them into elements. You're running the reaction backwards. And once you've got elements, you can turn them into products. So you're forming them. And the ends here just account for the fact that if you've got 2 moles or 3 moles or 3/2 of a mole, you need to multiply by that factor. One more thing here, the degree symbol up here indicates that we are under standard state conditions. So solids and liquids are pure, gases are at 1 atmosphere, and solids are at 1 mole per liter. So that's how we calculated delta H. Now we can calculate delta S of reaction using exactly the same idea. In fact, the third law of thermodynamics allows us to calculate the entropy of a substance, because the third law says that the entropy of a pure crystalline substance is 0 at absolute 0. So all you got to do is basically take the substance at absolute 0 and you heat it up. So basically you enter heat into it at a particular temperature and you calculate then every time you go up by 1 degree, how much heat did you put in at 1 degree, how much heat did you put in at 2 degree, and you sum it all up and you can get the entropy of a substance at any temperature you like. In fact, this can be tabulated. This is often tabulated at 298 Kelvin. And let me just kind of bring up a quick table and show you what I mean. So this table is in our textbook, it's in the appendix, it's also in the chapter, and it shows us for every substance what the standard molar entropy is. Sometimes we call these third law entropies because this was not accepted for a while, that at absolute 0 entropies were 0. And so a lot of people started referring to them as third law entropies just in case the third law was wrong, in which case we can say, well, those weren't real entropies, they were third law entropies. So at 298 Kelvin, we can see that gases have an enormous amount of entropy compared to liquids, which have more entropy in general compared to solids. So the more complicated the structure is, the more entropy it has. So gases are sort of wildly moving around, they're crazy, they're very complicated, a lot of entropy. Liquids, things are a little higgledy-piggledy, so a little less entropy than a gas, but a lot more than a solid, which is nice and crystalline and everything is nicely organized. We can certainly see the smaller the solid is in terms of formula, the simpler it is, the smaller the entropy is. So something like lithium and copper, very small entropy values. As we go to something like sodium chloride or calcium carbonate or iron chloride, the more complicated the formula, the more atoms and ions, the more entropy that we have created. The same with liquids here. So the bigger the liquid is in terms of number of atoms or in terms of the atomic weight of the atoms, the more entropy it has. Water has a surprisingly low entropy though, and that's because that even though in the liquid you might think it's higgledy-piggledy, those hydrogen bonds are causing the molecules to be held together in sort of like a fishing net structure, and that just gives it a little bit more order than you'd expect. If you look at gases, gases have a massively huge entropy. The bigger and more complicated the gas, the higher the entropy is. And so in general, gases are much bigger than liquids and solids, but you can find exceptions. So for instance, benzene is a liquid. It it has more entropy than hydrogen, a gas, and so on. Iron chloride, a solid there, has got more entropy than, say, hydrogen, a gas. So got to be a little bit careful, but you can always look this stuff up in a table. So let's go ahead and do a calculation and calculate delta S of a reaction from this data. So we would do the calculation exactly the same way we did the enthalpy calculation, and let's just write the equation down underneath. So delta S of a reaction is just the entropy of products all added up. So that would be the standard entropy of my products all added up. If I've got more than one mole, I got to remember to multiply by the number of moles. Subtract away from that the number of moles of my reactants all added up like so. So for example, we could take a chemical reaction, so something like 2FeCl3, and maybe break it down into a couple of irons and 3 chlorines. And we could calculate delta S of that reaction. So delta S of that reaction would just be 2 times the molar entropy of iron. We gotta look at the state symbols, but I'm too lazy to write them. 3 times the molar entropy of chlorine. And we subtract away from that 2 times by the molar entropy of iron 3 chloride. So we can look all of these up in the table above. And so iron has a very small entropy. It's 27.3 joules per mole Kelvin. Chlorine has a molar entropy of 223.1. And iron 3 chloride has a molar entropy of 142.3. So if I go ahead and just move this up slightly, I make that to be positive 439.3. I can spell that. And what are the units? The joules, the units would be joules per Kelvin. And the reason for that, I suppose, is that these would be the number of moles. So this would be 2 moles. This would have units of joules per mole Kelvin. The moles would cancel, and it would give you joules per Kelvin. There's actually a little bit of dissent in the community. So some people will actually say these are actually just numbers, and so this should have units of joules per mole Kelvin if that's the case. And some people will say that, no, those are the number of moles, and then it would be joules per mole Kelvin. And so you'll often see it written 2 different ways. Personally, what I'll do is I'll just kind of fix the units that are right. So whatever I'm expecting, I will make sure I see, but you didn't hear it from me, okay?